Welcome 10A students. Today we're going to be doing a worked example on related rates. So we are given that gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute, and its coarseness is such that it forms a pile in the shape of a cone, whose diameter and height are always equal. How fast is the height of the pile increasing when the pile is 10 feet high? I've taken the liberty of drawing up the diagram on the right. We have a cone whose height and diameter are both equal. So we're dealing with a cone, which means we'll need our cone formula, which is V equals 1/3 pi r squared times h. Let me just make these neater. Then we're also given that the diameter, which is 2r, is equal to the height. So another way of writing this is that r is equal to h over 2. Lastly, we want to know what, we're also given that the change in volume is equal to 30 cubic feet per minute. And this is a constant, it's not changing. Then the problem asks, what is the change in height, which is our dh over dt, when h is equal to 10 feet? Okay, so we've broken down the question. We found change in volume. We found a handy little parameter where we set our diameter and height equal to each other. We understand that we're looking for the change in height when the height is 10 feet. So let us begin by first replacing the r in our volume formula with this new h over 2. And this is so we can get our function of t for our volume, all with respect to one other unknown variable, in this case our h. We're going to go ahead and then simplify this. We're going to see that the 2 gets also squared, and we're going to multiply it with a 3 to get 1/12 pi h squared times h, and the h's can then be grouped together to h cubed. So now we have this function for the volume all in terms of one other variable, h. Now, keep in mind that this v is actually a function of t, and so is our h is a function of t. We want to derive both sides implicitly with respect to t. So that means we're going to get our dv over dt equaling, we're going to take the 3 from the h down, still having the coefficient 1/12 in pi, but then we're going to reduce the power on the h by 1, and then again, h is also a function of t, so we want to then write out dh over dt. So here you can go ahead and substitute in some values, but I'd like to first solve the equation for dh over dt. And that's simply moving all of this stuff tacked on the left side of it to the right, to the left, all of the stuff tacked on the left, move it to the left. Also, this 3/12 can be simplified to 1/4. So we're going to move all this over. We're going to get 4 over pi h squared dv dt, and this equals our dh dt. Okay. So we found an equation for the change in height with respect to t. And we also know all these extra little tidbits. We know what h value you want to plug in and what the change in volume is. So our dH dt becomes 4 times 30 over pi times 10 squared. We can simplify this. We can get rid of a 10, and then also the 10 goes into 12. Well, you can simplify them by 2, divide both by 2. And then we're left with 6 over 5 pi. And we're dealing with the change in height with respect to time. And the units we were using were feet per time unit minutes. So the final answer is the change in height of the pile is increasing by 6 over 5 pi feet per minute. Ta-da!